All right, so let's do one from yesterday or one similar to the ones from yesterday to bring us back into it. So these reactions right here, if we have something that gives us the delta H, if that delta H is positive, that means it's absorbing or it's endothermic. If that delta H is negative, that means it's losing that energy or it's exothermic. So let's calculate the amount of heat absorbed when 5.66 grams of carbon disulfide is formed. So carbon disulfide, di means 2. CS2 is what we're dealing with. We have 5.66 grams of that forming. We need to find out how many moles that is, because this, even though it doesn't say it, it should, is kilojoules per mole. If this were a 2 here, then once we figure out the number of moles, we would have every 2 moles makes that much. So just keep that in mind. Every 1 mole here for a CS2. And what's that? I'll go with it. Molar mass was given to me, so if that's incorrect, make sure you check it yourself. And every 1 mole of that is 89.3 kilojoules.
Oh, shoot. 77 chlorine.
One more time. Molar mass has been given to me again, and it's different, 76.10. So if we take a look here, obviously you should be able to find the molar mass. So I'm going with this new one. But if you've got something different, use it. Divided by 76.1 times 89.3. I think they are sleeping. I think they just turned me on and like nobody said anything. There's nothing in the chat. So is this 13. So we get we have 3 significant digits to start with. So we get 6.64 kilojoules. That stuff is pretty easy. So this is using the delta H of the reaction. Remember, it could be combustion, formation, all of these different types of reactions that they could give you a delta H on. If it doesn't say anything, we assume it's molar. Because it's not often that you have this written in per grams or anything, because these are not grams, these are moles, right? So it only makes sense. Brings us to today's discussion, heat of formation. So we talk about enthalpy being a state function. The cool thing about that means is that we get to determine, the bottom. And the bottom that scientists chose was elemental. So anything in its elemental form, whenever we talk about the heat of formation, it's already been formed. So its heat of formation would be 0. Now that is in its original, standard state. Is diamond the standard state of copper? No, right? It would be coal or graphite. Like those would be the standard states. So diamond does take a little bit of energy to organize those carbon particles to basically form that structure. So if you see diamond, it would not be 0. But things like H2, O2, gas, they would be 0. O2 liquid, no, that's not how oxygen is found at 25 degrees Celsius. So keep that in mind. If they give you a table like this and you are looking for something and you can't find it on that table, there's probably an element in its state, in its standard state. So you're not going to find O2 on this table. So yeah,
I just had a quick question. When it says like kilojoules per mole for the equation, is that per moles of like product, or what is that per moles of?
It's per moles of everything that they give you in the equation. So if you take a look, like for this combustion, it would be per mole of this. But whenever you use it, you have to deal with 5 moles of oxygen, right? So
Oh, I got you.
Yeah.
Okay, thank you.
it's a conversion factor where whatever the number of moles in the reaction are, it's kind of like every 5 moles of oxygen gives this. So if you were to do it per mole of oxygen, you would need to take this and divide it by 5. But there's no need to do that at the beginning or anything because you can just write it out like a normal conversion factor.
I got you. Thank you.
You're welcome. Again, it's also why sometimes they talk about like this is the molar heat of combustion for this. Luckily, everything here has a whole number, but a lot of times what they'll do is they'll make this 1. So you might see like something 0.5 or something and a half of oxygen and stuff like that, just to make sure that it's the heat of molar combustion for whatever you're combusting. I think that this actual sheet is pretty forgiving with that and giving you nice whole numbers. So with heat of formation, you take the heat of formation, basically the summation of the products minus the summation of the reactants. So given the heat of formation for CH4 being negative 75, carbon dioxide being negative 394, and water being negative 286, what do we do? Well, this is per mole, right? So that means that we have 2 moles of water plus 1 mole of carbon dioxide and we're going to subtract from that 1 mole of methane. Why don't I worry about the oxygen? It's 0 because it's the standard state of matter for O2, right? It doesn't say gas there, but we're assuming. So then we add this up. 2 times negative 286 plus negative 394 minus negative 75.
It's negative 891.
All right. 2 times negative 286 plus negative 394 minus negative 75. Boom. So whenever we combust 1 mole of methane, we get 891 kilojoules given off. It's exothermic, which makes sense because we're burning methane. We know that when we burn these organic compounds, a lot of times they release energy. Products minus reactants. So whenever we're looking up here, this is one way that they found the delta H of those reactions. Questions there? Now we're looking at ammonia. So when delta H values are given, NH3 is negative 46, NO2 is 34, H2O is 287. Again, no O2 is given. The other version of this problem would be they give you the heat of the reaction, and then they don't give you one of the other ones, and then you just turn it into a solving for X problem, right? Key thing here is with enthalpy, you take products minus reactants except for one thing. There's one that switches, and I don't know if you remember that from X chemistry, but it's basically whenever you're dealing with the bond dissociation energies, you actually take the bonds formed minus the bonds, the bonds broken minus the bonds formed. All right, so let's take a look here. We have NO2, we have 4 of those. 7. H2O, we have 6 of these. We're going to subtract then the reactants. All we got to worry about is the NH3. 4 times 34 plus 6 times negative 286 minus 4 times negative 46.
It's negative 1,396.
Boom, boom. This is a standard heat of formation table. You will be given this. Obviously, again, as you look, there are no elemental forms on there, but there are some tricks. Here we have H2O gas. Here we have H2O liquid. Strangely enough, a lot of times whenever they talk about combustion, I've noticed they actually use the liquid. In my mind, there's so much heat given off that it's usually in vapor, but from what I'm seeing is that a lot of times in the product side of a combustion reaction, they'll have this as H2O liquid. So just be careful of that. It will throw your answer off a little bit depending on how many moles are made. Maybe it's because they figure that they're forming these at standard temperature, but we know that if I ignite, let's say I ignite or combust hydrogen in the room back there, we're not going to get a bunch of water on the table. Okay? It's going to have enough energy to go up. Here's a bunch of these. As far as I know, as always, the answers here are correct. I will try to get the answers to this whole packet before Friday. We'll see. Hopefully. All right, let's take a look here. We comfortable with that? Yeah, all right. Hess's Law. Hess's Law is one of those things that is actually kind of fun. If you let it be. This is page 20. If you look at it like a puzzle, then it is a puzzle in a sense. Basically, you want to match 2 things to make one thing. Sometimes you match 3 things to make one thing. So if we take a look here, we have H2O liquid yields H2O gas. Since enthalpy is a state function, we don't care how we get here from here to here. As long as we look at it as here and here separately, then the combination of the 2 will get us where we want to be. So we know that we could take hydrogen and combust it in the presence of oxygen to get H2O gas. And we know we could take hydrogen and oxygen and combust it and get H2O liquid. So can we figure out, by knowing the amount of energy it takes to do each of these individually, how much energy it would take to go from liquid to gas? Well, the answer is yes. The man who came up with that was Hess. Basically, he opened up the door for the study of thermodynamics. Nobody understood that it was a state function and that you could make extrapolate this information like this. So if we take a look, we have H2O liquid on the reactant side here. Here we have it on the product side. So basically, we just need to flip this reaction so it is reversed. The other problem is we need to reduce it by, or divide it by 2. Because we only have 1 mole of H2O here. So we have 2 moles of H2O here. So if we divide this by 2, then we get H2O liquid, which is the only thing we're really concerned about, is getting this on the reactant side. So the fact that we've done that, we've switched it, means we switch the sign. We've divided it by 2, means we divide it by 2. 571.5 divided by 2.
It's 285.75.
So now it is positive, and it is half of what it used to be, because instead of having 2 moles of H2O liquid, we only have 1 mole. Now we got to get H2O gas on the product side. Well, we are there. The problem is we have 2 moles of H2O gas. So again, we want to divide this by 2. Negative 483.7 divided by 2.
It's negative 241.85.
We did not switch it. We did not reverse the reaction. So we still keep that negative, but we did divide it by 2. Now let us check. Anything that is on opposite sides will cancel out. So we have 1/2 O2 here, 1/2 O2 here. Those cancel. We have H2 here and H2 here. Those cancel. We get H2O liquid yields H2O gas. So basically, we add these 2 reactions together. Negative 241.85 plus 285.25.
The answer is 43.4.
So in order to go from H2O liquid to H2O gas, we need to input per mole 43.4 kilojoules of energy. Yeah. Easy enough. How many of you remember this from last time? It was easy then, or yeah? Okay. Those at home, you good with that? To tell you the truth, you can make this real hard with real weird stuff, but there's no need to do that. I mean, the AP doesn't do that. They make it hard with other weirdness. For example, they like this problem here. Write a balanced equation for the combustion of each of the following. So basically, you combust all of these except for water because that's not going to combust. And these are the enthalpy of combustion for those reactions. They then say, okay, you could make it this way. You can make ethanol this way. So calculate the standard enthalpy change. So you just made a bunch of reactions, these combustion reactions with these enthalpies, and you need to rearrange those reactions in order for it to make this equation right here. And then again, you would just add up those after those changes. So that's how they make it weird. They're multiple choice on this. It's garbage. It's too easy. So if we take a look here quickly, sometimes they are tricky. For example, here we have copper, 2 of them with copper on one side. So we would not want to go with that copper on that one side. If we take a look here, we have copper 2 oxide on the reactant side, but only copper 2 oxide on the product side for this one. So if we call this A and we call this B, what do we do to A? Not everybody at once. It's too loud. Just, yeah, flip it. Do we divide by 2? Maybe. I don't know. Yeah? He's pretty confident on that. Let's see. Dun, dun, dun. So we flipped it. So that makes this plus 310.5 kilojoules. I have a lot of trouble when I'm looking at things. So I have to cross stuff out. If you don't have to do that, you're probably better off not, because then you have that stuff from before. At this point, I have 2 of these, and I only have 1 here. The other problem is I have 4 of these coppers, and I have 2. So if we were to cancel this out right now, that would leave us with 2, right? So if we divide the top by 2, 310.5 divided by 2.
The answer is 155.25.
What can we do to the bottom one? I see here I have 2 copper 1 oxides, and only here I have only 1 copper 1 oxide. So what might I do to this one? Divide by 2. Negative 333 divided by 2.
It's negative 100.
And now if we add these together, my O2 cancel out. One of my coppers cancel out. And I think everything else is good. 155.25 plus negative 166.5.
The answer is negative 11.25.
Significant digit wise would be right there. Negative. I don't think they worry about significant digits on the AP exam, or they do care about it on the IB. Are you there today, Oscar?
Yeah.
All right, good, good. So the extra alarms helped, right? You made it.
Did.
I've got like 2 Alexas that fight each other in the morning to make sure that I make it up. They've only failed me once within, you guys remember that, last semester. What time's this thing over? Should we knock out the last type, or is that good for today? Louder? Knock it out. Gabe says knock it out. That will make tomorrow a review session then. So, the people that become suckers and people who play baseball are suckers. You getting a baseball scholarship? Do you think it's a possibility though? Okay, cool. I was just wondering, like, yeah, if you're not going to get a scholarship, whatever tomorrow, right? You don't need to be there at 5. Does Mr. Noble do anything with the baseball team anymore? No. It's basically Mr. McIntyre. All right. So as I told you, there's one last way to find this enthalpy, and that's by taking the bonds broken minus the bonds formed. We talked about this a little bit last week. We talked about that bond energy and how as we get closer to, the atoms get closer to each other, it requires you to put energy in. And there is this potential energy right there when they find that sweet spot that basically, if we take a look, this would be the atomic radii. And that's that energy that basically is holding them together. To pull them apart, it takes energy as well. And that's where you get the bonds broken part. So as you pull them apart and you reform them, they reform a lot of times. The universe has them reform naturally in a lower state. So that means if we take a look at where they were and the distance there, that's the energy when they form that's given off. There's a lot of trifle, like a word where you're like butting heads. They're trifling. Like there's a lot of trifle between chemists and biologists because they've taught you all your life that ATP energy is stored within the bonds. And in reality, you cannot say that bonds have, it's hard to say that bonds have stored energy because it takes energy to break the bonds. And when they reform, that's when that energy is released. It's easier to think about it almost as thinking of gravity. We know that the Earth and Moon have this attraction to each other. We know that atoms have this attraction to each other. If we were to try to move the Earth away from the Moon or vice versa, we would have to put energy into it. And then whenever that new, gravitational pull or whatnot gets back or whatever, that's kind of where it doesn't work with gravity, but it does work with atoms. Is wherever that new state is, that energy from here to there, when they reform, that's what energy is given unto the universe. The concept itself is a lot harder than any of the work you have to do to find the enthalpy, just like anything else. Basically, you have to be able to sit here and go, okay, these guys are the products, these guys are the reactants. So what are the bonds that we're breaking? Well, it's the bonds in this methane that we're breaking. Well, what do the bonds in methane look like? Well, we have to know the Lewis structure. So we have 4 carbon-hydrogen bonds that we need to break. So if we take a look, every 1 carbon-hydrogen bond has 411 kilojoules per mole. I'm just going to put kilojoules because I only have 1 mole of it. Here I have Cl2. I have 1 Cl-Cl bond, but I have how many moles of it? 2. Right? Every 1 Cl-Cl bond has 240 kilojoules of energy per mole. I have 2 F2 bonds. Every F bond has 155 kilojoules per mole. Now, that's the energy required to break all these bonds. When we reform them, we now need to subtract the energy of the reformed bonds, and that will tell us how much energy is available. So I have CF2Cl2. So I have 2 CF bonds. They are 485 each. I have 2 Cl bonds. 2 CCl bonds. 327 each. I have 2 moles of HF. 565. You know, it's cool. Most of you guys are seniors, so those guys can be like drive in late. Let them in from the. Yeah, don't do that. That's wrong. Tomorrow, right? HF. Is that where I'm at? I get something on my mind and I lost. I'm at the last one. HCl, right? 2 HCl bonds. 428. Whew. All right. We're going to do this in 2 parts. 4 times 411 plus 2 times 240 plus 2 times 155.
It's 2,434.
What did she say? All right. Make sure this is right. Oh, come on, come back. All right. Again, make sure you understand that all of these are positive, which basically means we are putting in that energy to break these, right? And we are subtracting this energy from that to figure out how much will be left over. 2 times 485 plus 2 times 327 plus 2 times 565 plus 2 times 428.
That would be 3,610.
$2,434 minus 3,610.
It's negative 1,176.
Boom. So that means that this equation has a delta H of negative 1,176 kilojoules. So if we found this and then somebody said, well, what if we have 70 grams of chlorine reacting and excess all the other ones? We could figure out the energy that would be given off with that 70 some grams of chlorine reacting. So there's 3 ways to determine enthalpy. Two of those ways, energy of formation, well, all of these ways actually allow you to figure out the enthalpy of a reaction. Heat of formation allows you to use a table that has the standard enthalpies of formation. Those are averages, by the way. Depending on, they call it standard, so at 25 degrees. But, these also are averages. For example, if we take a look, you can imagine that the energy required to break a hydrogen-oxygen bond in H2O, that's just an average, that 459. In reality, to break the first one would take more energy than the second one. So, I mean, just keep in mind that these are averages. So this will get you about that, right? But that's it. We have the way to break the bonds and reform them and figure out approximately the delta H of reaction. We have a way to look at many different reactions and pathways and put them together in one to find the delta H of the reaction. And we have the way to use a table of standard heats of formation to take the products minus the reactants and determine the delta H of a reaction. Bada bing, bada boom. Use the rest of the time to work on a few of these different types of problems. Tomorrow, basically, I'll work through some problems with you, and those of you that come to class or whatever, I'll work through some problems, videotape myself doing it. That way you can check your work on it. Other than that, have a great day at home. If you have questions, as always, stick around. Hopefully you guys are doing good at home. How was your guys' lunch yesterday? Bad? Weird? It wasn't enough. Somebody's an athlete. They play baseball. There wasn't enough food there? What's that? Oh, that's Gabe. With the masks, I can't tell. Have a great day, guys. Get out of here, or you can stick around and listen to the banner. Otherwise, I'm stopping the recording just in case I say something.